I'm Suma Priya from KL University, and today I'll be presenting my internship project completed at Emertxe Embedded Systems. The title of my project is EV ADAS Dashboard using STM32, PICSimLab, and Python. This project focuses on developing a real time vehicle telemetry visualization system by integrating embedded firmware, UART communication, hardware simulation, and Python based dashboard. Throughout this project, I'll explain the motivation behind the project, the system architecture, implementation process, challenges, testing results, and finally demonstrate the complete working system. Before discussing the project, I'd like to briefly introduce the internship and the skills I gained during this journey. Emertxe Embedded Systems is a training organization that focuses on practical embedded system development through industry oriented projects. During this internship, I gained hands on experience in embedded C programming, STM32 microcontroller programming, UART communication, hardware abstraction layer, debugging, and system integration. One aspect I appreciated about this internship was that it emphasizes solving engineering problems rather than simply writing code. Every module we developed followed a structured workflow, including understanding the problem, designing the solution, implementing it, debugging communication issues, and validating the complete system. This project allowed me to combine embedded firmware with Python visualization, giving me exposure to both embedded software development and desktop application integration. These are the skills that are widely used in automotive electronics, industrial automation, and IoT systems. Since this project is based on automotive embedded systems, it's important to understand why embedded system and ADAS are so relevant today. An embedded system is dedicated computing system designed to perform specific function within a larger system. Unlike general purpose computers, embedded systems are optimized for reliability, efficiency, and real-time operation. They are present in almost every modern electric device, including automobiles, medical equipment, industrial machines, aerospace systems, and consumer electronics. In the automotive industry, embedded systems control components such as engine management, braking systems, airbag deployment, battery management, and infotainment systems. Advanced Driver Assistance Systems, or ADAS, use embedded systems to improve vehicle safety by monitoring the surrounding environment and assuming the driver. Features such as obstacle detection, blind spot monitoring, collision warning, and lane assistance are all examples of ADAS. As electric vehicles became more intelligent, the amount of data generated by these embedded systems continued to increase. This creates a need for efficient visualization tools that help engines monitor and analyze the vehicle telemetry in the real time. That need motivated the development of this project. After understanding the background, let's look at the specific engineering problem that this project addresses. During embedded system development, firmware continuously generates large amount of telemetry data. Traditionally, this information is viewed through serial terminals as plain text. Although this approach is useful for debugging, it becomes difficult to interpret multiple parameters simultaneously. Engineers need a better way to monitor vehicle behavior while testing firmware. Therefore, the objective of this project was to develop a real time dashboard capable of receiving UART telemetry from STM32 microcontroller and converting it into meaningful graphical information. The dashboard should display speed, battery percentage, motor temperature, torque, acceleration, braking, obstacle distance, blind spot detection, collision warning, and fault information. At the same time, the system should remain modular so that simulated hardware can later be replaced with physical hardware without changing the visualization software. Once the objective were defined, the project was developed following a structured engineering process. To ensure systematic development, I followed a software development lifecycle approach. The first phase was requirement analysis, where I identified the project objectives, communication requirements, and visualization needs. Next came the system design, where the overall architecture, communication pipeline, and dashboard modules were planned. During the implementation, I developed the STM32 firmware configuring UART communication, establishing a virtual COM port communication using VSPE, and built the Python dashboard. Each module was tested individually before integrating the complete system. After integration, several debugging sessions were required to resolve UART communication issues, virtual COM port configuration problems, and packet synchronization errors. Finally, the system validated at PICSimLab simulation to verify that telemetry was transmitted and visualized correctly. Following this structured approach helped me ensure reliable integration between the system components. Now that we've covered the development process, let's move to the technical foundation of the project and look at the technologies that we have used. This project combines multiple technologies, each selected for a specific purpose. At the embedded layer, I used STM32 Blue Pill microcontroller programmed using Embedded C in STM32 Cube IDE. HAL drivers were used to simplify peripheral configuration and improve code portability. UART was selected as the communication protocol because it is simple, lightweight, and widely used for embedded debugging and device communication. Since physical hardware was not available, PICSimLab was used to simulate STM32 microcontroller and execute the firmware in a virtual environment. VSPE created a virtual COM port pair allowing the serial communication between the simulator and Python application. On the software side, Python was used with PySerial for serial communication, regular expressions for packet parsing, NumPy for data handling, and Matplot library for graphical visualization. The combination of these tools enabled the complete embedded desktop communication pipeline. The overall system architecture. This process begins with STM32 firmware, which generates simulated electric vehicle telemetry such as speed, battery percentage, motor temperature, torque, acceleration, braking, and ADAS related information. These values are formatted into UART packets and transmitted at baud rate of 115200. PICSimLab simulated the STM32 hardware and forward the UART output to a virtual COM port. VSPE bridges this communication from COM11 to COM12, allowing the Python application to receive the data. The Python backend continuously reads the incoming serial packets, validates them using regular expressions, extracts the required parameters, and updates a centralized dashboard state. Finally, the visualization engine refreshes gauges, graphs, obstacle indicators, blind spot detection, alarm, and faults information in real time. One important design decision was to separate firmware generation from dashboard visualization. This modular architecture allows the dashboard to work either simultaneously simulated hardware or physical STM32 board without significant software changes. Firmware and Python architecture. The project consists of two major software components, the embedded firmware and Python application. On the firmware side, the STM32 initializes the system clock, GPIO, and UART peripherals. Once initialization is complete, it enters an infinite loop where telemetry values are generated, formatted into structured packets, and transmitted through UART using HAL UART transmit function. On the Python side, I adopted a multi-threaded architecture. A dedicated serial thread continuously reads incoming UART packets without blocking the user interface. The received packets are validated using regular expressions converted into structured data and stored in shared state. The GUI thread then retrieves this updated data and refreshes the dashboard components independently. This separation between communication and visualization ensures smooth real-time updates while preserving the interface from freezing. UART communication and data flow. UART is an asynchronous serial communication protocol widely used in embedded systems because of its simplicity and reliability. In this project, UART communication was configured with a baud rate of 115200 using the standard 8-bit data, no parity, and one-stop bit configuration. Instead of sending all telemetry in a single message, I divided the information into two packets. The first packet contains vehicle parameters such as speed, battery percentage, torque, temperature, range, acceleration, and brake percentage. The second packet contains ADAS related parameters including obstacles distance, time to collision, collision status, blind spot detection, alarms, and false codes. The Python application continuously receives these packets, validates their format using regular expressions, extracts the required values, and updates the dashboard accordingly. Dividing the data into two packets improves readability and simplifies packet parsing and synchronization. The project workflow. This slide summarizes the complete operational workflow. The STM32 firmware first generates simulated telemetry values. These values are transmitted through UART and forwarded by PICSimLab to a virtual COM port. VSPE bridges the communication to another COM port monitored by Python application. The Python backend reads the incoming packets, validates the and parses the telemetry and updates the dashboard state. Finally, the visualization layer refreshes all the graphical components including gauges, graphs, obstacle indicators, and warning messages. This end-to-end pipeline demonstrates successful integration between embedded firmware, simulated software, communication middleware, and desktop visualization. After establishing the complete communication pipeline, I'll now demonstrate the features implemented in the dashboard and discuss the engineering challenges that I have encountered during the development. Dashboard features. This slide showcases the final dashboard development during this project. The dashboard provides a real-time visualization of important vehicle parameters. These include speed, battery percentage, remaining range, temperature, torque, acceleration, brake percentage, and speed history graph. In addition to vehicle telemetry, the dashboard also displays ADAS information such as front obstacle distance, blind spot detection, collision status, time to collision, alarm levels, false codes, and drive mode. Instead of interpreting raw serial data, engineers can instantly understand the vehicle's condition through intuitive graphical components. This significantly improves monitoring, debugging, and system validation. Challenges. During the development, the biggest challenge was establishing the reliable serial communication between the simulator and the Python application. Initially, I encountered a UART timeout error, semaphore timeout issues, virtual COM port configuration problems, and incomplete packet reception. To resolve these issues, I carefully configured the VSPE virtual COM ports, implemented proper packet formatting, used regular expressions for robust parsing, and separated communication into two structured packets. Another challenge was preventing the dashboard interface from freezing during continuous serial communication. This was solved using dedicated serial thread for communication while the GUI updated independently. These debugging experiences help me understand how communication reliability is just as important as writing the fire firmware itself. Testing and results. Once all the modules were integrated, the complete system underwent multiple levels of testing. Individual models such as UART communications, packet parsing, and dashboard visualization were tested independently before system integration. End-to-end testing confirmed that telemetry generated by STM32 simulation was successfully transmitted, received, parsed, and displayed on the dashboard. The communication pipeline remained stable during continuous operation, demonstrating successful integration between all the project components. This internship significantly improved both my technical knowledge and problem solving abilities. I gained practical experience in embedded C programming, STM32 development, UART communication, HAL drivers, Python programming, serial communication, multithreading, regular expressions, debugging, and system integration. More importantly, I learned how individual modules interact to form a complete embedded system, and how structured debugging and modular design simplify complex engineering projects. Although this project was developed as a simulation based prototype, the architecture is applicable to real world automotive systems. Similar communication pipelines are used in electric vehicles, digital cockpits, vehicle diagnostics, fleet management systems, and automotive testing environments. Future improvements include UART and CAN bus integrating free RTOS for real time scheduling, connecting physical sensors and adding GPS, cloud connectivity, implementing AI based predictive maintenance, and supporting the over the air software updates. These enhancements would make the system even closer to production grade automotive solution. To conclude, this project that successfully demonstrated the integration of embedded firmware, serial communication, simulation, and desktop visualization into a unified ADAS dashboard. The project, the project not only achieved its technical objectives but also strengthened my understanding of embedded systems communication protocol, debugging and strategies, and system architecture. Overall, this internship provided valuable hands on experience that bridges academic learning with real world engineering practices. Thank you for the time and attention. Now, I'll be demonstrating the complete implementation of this project. The project consists of four major components that work together: STM32 firmware, PICSimLab hardware simulation, VSPE virtual serial communication, Python based EV ADAS dashboard. I'll explain how each component contributes to complete the communication pipeline before showing the live dashboard. Now, this is the STM32 firmware. This firmware is developed in STM32 Cube IDE using Embedded C. The STM32 microcontroller acts as telemetry generation unit of the entire system. After initialization, the firmware configures the system clock, GPIO, and UART peripherals. Once initialization is complete, the program enters an infinite while loop. As shown, inside this loop, simulated vehicle parameters are generated continuously. These parameters include vehicle speed, battery percentage, remaining range, torque, motor temperature, acceleration, brake percentage, obstacle detection, blind spot detection, and alarm level fault code. These values are formatted into structured UART packets using string formatting functions. Finally, the packets are transmitted through UART using HAL UART transmit function at the baud rate of 115200. At this stage, the firmware's responsibility is complete. It simply generates and transmits telemetry continuously. Since I'm working in simulated environment, instead of using physical hardware, The components is in PICSIM laboratory, which are PICSimLab simulates the STM32 Blue Pill microcontroller. Instead of uploading firmware to a physical development board, the compiled firmware runs inside the simulator. The simulator executes the same embedded code exactly as the hardware would. The UART output generated by firmware is redirected to the virtual COM port. This allows the firmware to communicate with external software without required any physical serial cable. Using PICSimLab significantly reduces hardware dependency during development and debugging while providing a reliable testing environment. However, the simulator alone cannot communicate directly with the Python application. For that, I have used VSPE. VSPE stands for Virtual Serial Port Emulator. It creates a virtual pair of COM ports. In my implementation, PICSimLab transmits telemetry through COM11. VSPE creates a virtual bridge between COM11 and 12. The Python dashboard listens on COM12. The virtual serial bridge behaves exactly like a physical serial cable. It enables reliable communication between the embedded firmware simulation and the desktop application. As it's shown right here, the connections and the device. Once the communication channel is established, the Python dashboard starts receiving the telemetry. This is the Python-based EV ADAS dashboard. The application continuously listens to the incoming serial data through COM12 using PySerial library as shown in the terminal right here. A dedicated background thread reads incoming packets without blocking the graphical interface. The received packets are validated and parsed using regular expressions. After parsing, the extracted values are stored in centralized dashboard state. The visualization engine continuously refreshes the graphical components using the latest telemetry. Speedometer. This gauge displays the current vehicle speed received from STM32 firmware. Battery. This panel shows the battery state of the charge. Currently, the firmware transmits a constant SOC value for demonstration purpose. Remaining range. The remaining driving range is also transmitted by the firmware. Similar to the battery percentage, this value remains constant in the current implementation. Motor torque. The motor temperature updates continuously and represents simulated thermal conditions. Torque. This indicates temperature displaced and the simulated motor torque generated by the firmware. Speed graph. The graph continuously plots vehicle speed over time. It helps visualize speed variations instead of showing only the current value. Bird eye view. This module provides a simplified representation of vehicle surroundings. Obstacle detection, front obstacle distance is displayed right here. As the distance decreases, warning conditions become active. Blind spot detection. The left and right blind spot indicators notify whether a nearby obstacle are detected. Time to collision. TTC estimates the time remaining before potential collisions based on the incoming telemetry. Alarm system. Different alarm levels indicate the severity of the detected situation. Fault code. Fault code simulate vehicle diagnostic messages similar to those used in modern automotive ECUs. Driver mode. The dashboard also displays a currently selected driving mode. Together, these components provide engineering with a complete visualization of the vehicle state instead of relying on raw serial logs. To summarize this complete workflow, the STM32 firmware generates simulated vehicle telemetry. The firmware transmits the telemetry using UART. PICSimLab executes the firmware and forwards the UART output to COM11. VSPE bridges COM11 to COM12. The Python application continuously receives the data through COM12. Regular expressions extract telemetry values. Finally, the dashboard updates all graphical components in real time. This demonstrates successful integration of embedded firmware, serial communication, simulation software, and desktop visualization into a complete system. This completes the implementation of demonstration of my EV ADAS dashboard. Through this project, I gained practical experience in embedded C programming, STM32 development, UART communication, debugging, hardware simulation, Python integration, and real-time visualization. Thank you for your attention.